Hello, coders, and welcome. I'm NerdTeach, and I'll be your guide through the world of computer science. Today, we're going to tackle a topic that, let's be honest, often feels like a huge hurdle for new programmers: recursion.
So let's just start by addressing the elephant in the room, shall we? Why does this one concept seem so confusing at first? I mean, a function that calls itself, it sounds like a paradox, right? Something that should just create an infinite loop and crash everything. It feels a bit like, well, like magic.
My mission today is to completely change that for you. We're going to break this thing down, logically, piece by piece. We're going to strip away all that magic and reveal the simple, elegant machine that's actually running underneath it all.
All right, so let's dive in. Before we even think about looking at a single line of code, the most important thing we can do is build the right mental model. So for a minute, I want you to stop thinking like a computer, just executing a list of commands, and let's start thinking more strategically about how we solve really big problems.
You know, most of us are really used to thinking in loops, what we call iteration. A for loop thinks, okay, I have a task, and I'm just going to repeat these steps until it's done. It's very direct, very step by step. Recursion, though, is a fundamentally different approach. It is all about delegation. A recursive function basically says, look, this whole problem is way too big for me to solve all at once. So here's what I'll do. I'll handle one small piece right now, and then I'm going to pass a slightly smaller, simpler version of the problem to an identical copy of myself, and I'm just going to trust that that copy will give me back the answer I need.
What's really fascinating is that this idea of trusting a smaller version of yourself isn't just some clever programming trick. It's directly inspired by a really powerful concept from mathematics called mathematical induction. Now, don't let the name scare you. The idea behind it is actually very simple, and it's all about proving that a chain reaction is guaranteed to work.
Just think about a long line of dominoes. If you want to prove to someone that all of them are going to fall, you don't actually have to push each one and watch. You only need to prove two things. First, that you can for sure knock over the very first domino. That's what we call the base case. Second, you have to prove that if any domino falls, its fall will absolutely cause the next domino in line to fall. That's the inductive step. If you can prove those two things, you've just proven the entire chain reaction works, without a doubt.
And that domino principle, that's the exact mental model we need for recursion. Recursion is just that same logic, the base case and the inductive step, translated into the structure of a function. So let's break down what that structure looks like.
Every single properly written recursive function is built on two essential parts, and they perfectly mirror our domino proof. You have the base case, which is your first domino, the one that starts it all and stops the chain, and you have the recursive step, which is the guarantee that one domino will successfully knock over the next.
Now, the base case is without a doubt the most critical part. It is the function's absolute, non-negotiable stop sign. It represents the smallest, simplest possible version of the problem, a version so easy the function can solve it immediately without any more help. Without a base case, the function would just call itself forever and ever, leading to a really common and frustrating crash called a stack overflow.
Okay, so what if the problem isn't the simplest version? What if it's not the base case? Well, that's when the function performs the recursive step. And this step really has two jobs. First, it breaks the problem down, making it just a little bit simpler. We call that decomposition. Then it calls itself with that new, smaller piece. This is the delegation, the self-reference part. It's trusting that this next call in the chain will get us one step closer to finally hitting that base case.
All right, enough theory. Let's move to a classic example and see how all of this builds into actual code. We're going to look at calculating the factorial of a number. It's a perfect fit for recursive thinking, because think about it, the factorial of 5 is really just 5 times the factorial of 4. See that? The problem's definition includes itself. That's a huge clue that recursion is a good fit. So here's a pretty standard function in C++ to calculate factorial. I want you to just look at its structure. It's basically asking one simple question: am I at the base case yet? If the answer is yes, great, it stops and gives back an answer. If the answer is no, it does the recursive step. You can literally see those two pillars we just talked about mapped directly to the code.
And this just brilliantly shows the two distinct jobs of this function. That if n less than or equal to 1 block, that's our stop sign. That's our base case. It's the simplest version of the problem we can solve. The factorial of 1, or even 0, is just 1. We're done. No more calls needed. But that second line, return n times factorial n minus 1, that is the delegation. It does one small piece of work, it holds on to the current number n, and then it delegates the rest of the problem, factorial n minus 1, to another identical function call.
Okay, but how does this not create total chaos? How does a function that calls itself remember what the value of n was in the previous call? Well, the magic here is something called the call stack. This is the memory structure in the computer that makes all of recursion possible.
The call stack is kind of like the computer's short-term memory, just for functions. It works exactly like a stack of plates. The last one you put on is the first one you take off. When any function is called, a new plate, or what we call a stack frame, gets pushed onto the top. This frame holds all of its local variables. So let's trace factorial of 3. First, a frame for factorial of 3 gets pushed onto the stack. It asks itself, is 3 less than or equal to 1? Nope, so it knows it needs to call factorial of 2.
And right at that moment, factorial of 3 just pauses. It freezes and waits for an answer. A new frame, this time for factorial of 2, gets pushed on top of the stack. Now, factorial of 2 is in control. It does its own check, sees that 2 is also not the base case, and so it gets ready to call factorial of 1.
So, factorial of 2 also pauses, waiting. Finally, a new frame for factorial of 1 is pushed onto the very top of our stack. Now, factorial of 1 takes control. It looks at its condition, if n less than or equal to 1, and this time, it's true. We did it. We've hit the base case.
This right here is the turning point. The chain of delegation, of making new calls, finally stops. This whole process of pushing new calls onto the stack, going deeper and deeper, is called the winding phase. Now that we've hit our stop sign, we begin the unwinding phase, where the answers get passed back down the chain.
So factorial 1 doesn't make any more calls, it just returns the value 1. And where does it return to? It returns to the function that called it, which is sitting there waiting right below it on the stack, factorial 2. The factorial 1 frame has done its job, so it gets popped off the stack. Now factorial 2 wakes up, gets that return value of 1, and it can finally finish its own calculation. 2 times 1, which is 2.
And now, factorial of 2 is done. It returns its result, 2, back to its caller, which was factorial of 3. Then, the factorial of 2 frame gets popped off the stack. So finally, factorial of 3, which has been waiting this whole time, receives the answer it needed. It takes that 2 and completes its calculation, 3 times 2, which is 6. At last, factorial of 3 returns 6 to whatever part of the program originally called it, and its frame is popped off. The stack is empty. Understanding this process, the winding and the unwinding, that is the key to removing all the mystery. It's not magic, it's just a very organized system.
Okay, so now that we've seen how recursion works when everything goes right, let's take a quick look at the common pitfalls that can really trip up beginners.
When recursion goes wrong, it almost always causes that stack overflow error we talked about. This happens for a few key reasons. The most obvious is just a missing base case. The function literally has no stop sign. But a more subtle error is what we call no progress. This is when your recursive step doesn't actually make the problem any simpler. Imagine if we accidentally wrote factorial of n inside a factorial of n. The input never changes, so it can never ever reach the base case. That's a true infinite loop.
So now that you know how it works and what to avoid, you might be asking, okay, where is this actually useful? Why learn this whole new way of thinking when I can just use a loop? That's a great question.
Recursion really shines when you're dealing with problems that have a nested, or what we call a self-similar structure. The absolute best example is your computer's file system. Think about it. A folder can contain files, but it can also contain other folders which then contain more files and more folders. To write a program that finds a specific file, the logic is naturally recursive. Search this folder. For any item that's a file, check its name. For any item that's another folder, run this exact same search logic on that subfolder. Trying to do that with loops gets very messy, very fast. But with recursion, the code is clean and elegant precisely because it mirrors the structure of the problem itself.
And that right there brings us to the job interview. Interviewers absolutely love recursion questions. And it's not to trick you, it's to test something fundamental. Can you take a big, complex problem and break it down into the simplest possible version of itself? That skill, that way of algorithmic thinking, is what they're really looking for. So let's put everything we've learned into a simple mental checklist. The next time you face a new problem, I want you to ask yourself these 3 questions to see if recursion might be a good fit. Number 1, what is the absolute simplest input for this problem, the base case, the stop sign? Number 2, can I solve the bigger version of the problem if I just assume I already have the answer to a slightly smaller version? And number 3, and this is crucial, does every single recursive call I make get me one step closer to that stop sign? So there you have it.
We've demystified the logic, we've visualized the mechanics of the call stack, and we've armed you with a mental checklist. Recursion is no longer magic, it's a powerful, elegant tool in your programming toolbox. The next time you see a problem with a nested or self-similar structure, don't shy away from it. Embrace that recursive mindset.
Today, we're going to tackle a topic that trips up so many developers: recursion. We're going to pull back the curtain, pop the hood, and see exactly how it works inside the machine. No magic, just mechanics. So here's our game plan. First, we'll talk about why recursion feels so weird and unpredictable. Then we'll reveal the secret weapon the computer uses to handle it all, the call stack. We'll watch a function go through its two phases, winding up and unwinding, and trace it step by step. After that, we'll cover the common mistakes that lead to crashes, and finally, we'll see why knowing all this is absolutely crucial for your career. By the end of this, you're going to feel so much more confident. Okay, let's dive right in with the core problem. This feeling of magic when a function just calls itself. You're not alone if you feel this way. I mean, the logic seems simple enough, right? A function calls itself until it hits a stop condition. But when you run it, somehow, poof, the right answer just appears at the very end. It really does feel like it's all happening inside some kind of magic black box. Well, today, we're going to pry open that black box. We're going to look directly into the computer's memory and watch this process unfold one step at a time. The magic is about to disappear and be replaced by something much better: understanding. So, the secret to it all? It lies in a fundamental part of how programs run, a memory structure called the call stack. Think of the call stack like a stack of plates in a cafeteria. You put a clean plate on top, then another, then another. The last plate you put on is the first one you have to take off. That's last in, first out, or LIFO. This is the golden rule. The newest function call that comes in is the very first one that has to finish and leave before anything below it can get back to work. And each of those plates has a name, a stack frame. Every single time a function is called, the computer creates one of these frames. Think of it as a personal, temporary workspace just for that one specific call. It's got everything it needs to do its job, and it's totally separate from all the others. Now, what's inside this workspace? Well, a few key things. It's got the parameters passed into the function, like the number n. It holds any local variables created inside, and, crucially, it remembers the return address, where to go back to when it's done, and the exact line of code it needs to resume from. This whole setup is why recursion works. Each call to the function gets its own set of variables in its own frame. They don't interfere with each other. So, because of this stacking process, every recursive function really has a two-part journey. It dives down, and then it comes all the way back up. And this is the million-dollar question, right? If we just keep stacking up function calls, one on top of the other, what stops the whole thing from just crashing? How does any actual work get done? It all comes down to this life cycle. First is the winding phase. This is where the function keeps calling itself, and for each call, a new frame gets pushed onto the stack. The key here is that each calling function is paused. No math is happening yet. Then you hit the base case. This is the stop sign. It's the turning point. And that triggers the unwinding phase. Now, frames start getting popped off the stack, and as they do, those paused calculations finally get to resume and finish their work. Okay, theory is great, but let's make this real. We're going to trace the function factorial of 3 step by step and watch what happens to the call stack. This table is going to be our guide. Just look at that return value column. See how it's pending for the first few steps? No actual answers are calculated until we hit that base case in step 3. Everything before that is just setting up the work. Okay, step 1. The first call, factorial of 3, gets pushed onto the stack. Let's ask our key questions. Where are we? We are inside the factorial of 3 function. Why hasn't the multiplication happened? Because it can't. It needs the result from factorial of 2 first. So what's it doing? It's paused. It's just sitting there, waiting for factorial of 2 to return a value. So, to get that value, we call factorial of 2. A brand new stock frame gets pushed on top. Where are we now? We are inside factorial of 2. The factorial of 3 frame is still there, just frozen underneath. And guess what? Factorial of 2 has the same problem. It needs the result from factorial of 1, so it also pauses, waiting. And that leads to step 3. We call factorial of 1. This is the big moment. It hits our base case. It doesn't need to call itself again. It just knows the answer, 1. This is the turning point. The winding stops. The stack is at its deepest point, and now the unwinding can finally begin. So, factorial of 1 returns the value 1. Its job is done, and its frame is popped off the stack. Poof, gone. Where does control go? Back to the frame that was waiting for it, factorial of 2. Now that it has the value 1, it can finally complete its paused calculation. It computes 2 times 1 and gets 2. The wait is over for this frame.
And now we repeat the process. Factorial of 2 returns its result, 2. Its frame gets popped off the stack. And where are we now? We're right back where we started, in the original factorial of 3 frame, which has been patiently waiting this whole time. It finally gets the value it needed and can calculate its final answer, 3 times 2.
And there it is, 6. Not from magic, but from a very orderly, predictable process of stacking up tasks, pausing them, and then resuming them one by one as the answers come back. Now that you see that step-by-step process, it becomes way easier to understand the common traps and mistakes people make.
The big ones are thinking these calls happen at the same time. They don't. It's strictly one after another. Another's expecting a value right away. Nope, you only get answers during the unwinding phase. But the most dangerous one is forgetting that stack memory isn't infinite. That leads to a very famous and very frustrating error.
So why did we just spend all this time in the weeds of computer memory? Because this isn't just theory. This is a practical, critical skill. I guarantee you, at some point in a technical interview, you'll get a question just like this. They're not just testing if you can write the code. They're testing if you understand what the computer is actually doing. Knowing this is what separates the pros from the people just guessing. And here is the ultimate real-world consequence. If you write inefficient recursion, like for calculating Fibonacci numbers, the number of calls can explode. Each one of those calls eats up a little bit of stack memory. If your recursion goes too deep, either because it's inefficient or you forgot a base case, you will literally run out of memory. And that crash, that is the infamous stack overflow error. So that brings us to the final thought. Now that you can literally see the stack filling up with frames, you can start thinking differently. How could you solve the same problem without piling up so much pending work? Understanding the problem is always the first step to finding a better solution.
How you can write powerful recursive functions that can chew through massive inputs without, blowing up your entire program.
And this quote, it just nails it. Most recursion mistakes happen not while you're typing, but when you're just thinking about it. When your recursive code fails, it's almost never a simple typo, right? The real bug is in how we're picturing the execution in our heads. So today, our mission is to fix that mental model. You're going to learn how to see recursion clearly.
And yeah, the biggest mistake of all is just not thinking about memory. That's what this all comes down to. We're going to look at the huge difference between what I call safe recursion and, well, explosive recursion. One is basically a super efficient loop in disguise. The other, it's a ticking time bomb, just waiting to crash your program with a Stack Overflow. Okay, so here's the game plan. First, we'll look at the hidden crash, a problem we've all run into. Then, we'll get into the solution. What is tail recursion? After that, we pull back the curtain on the compiler's magic trick. We'll follow that with a tale of 2 languages, and even see Java's trampoline solution. And finally, we'll wrap it all up with code that thinks ahead.
All right, first up, the hidden crash, the true price of elegance.
So why does this elegant-looking code crash? Come on, you've been there. I know you have. You write this beautiful recursive function, it works perfectly for like 5 or 10, but then you feed it 50,000 and poof, the whole program just dies. What is going on? Well, the culprit is something called the call stack. The easiest way to think about it is like a stack of plates. Every time a function calls another function, you put another plate on top. So with our standard recursion, factorial of 5 calls factorial of 4. But here's the thing. Factorial of 5 can't finish its job until it gets an answer back from factorial of 4. So it has to wait. It puts its plate on the stack and just sits there. And that's just the start of this chain reaction, right? Factorial of 4 calls factorial of 3, which calls factorial of 2. And with every single one of these calls, that stack of plates gets higher and higher and higher. It's just growing deeper, eating up more and more memory. Every plate is just waiting for the one above it to finish up and come back. Until it happens. Stack overflow error, bam, you've hit the ceiling. See, the stack isn't infinite. It has a hard limit. And when you run out of room to add more plates, the whole thing just comes crashing down. And this isn't some random bug. It's a fundamental problem with how this kind of recursion is designed. So, that's the problem. And it's a big one.
How do we fix it? Well, the key to optimization lies in a specific structure called tail recursion.
So what exactly is tail recursion? It's actually a pretty simple idea. It's when the recursive call is the absolute final action a function performs. That's the key. There is no other work to be done after that call returns. The function does its calculation, makes the final call, and its job is completely 100% done. And this comparison right here shows it perfectly. Let's look at the non-tail version on the left. See how the work, that n times part, happens after the recursive call comes back? That's the problem. The function has to hang around, keeping its plate on the stack, just to remember what n was. But now look at the tail recursive version on the right. All the work happens before the call. We do the multiplication right there in the arguments. The function basically says, here's the new result, go figure out the rest, I'm out of here.
Now, writing your functions this way isn't just a style choice. It actually unlocks something I like to call the compiler's magic trick, tail call optimization, or TCO for short.
So this is where the real magic is. The compiler is incredibly smart. First, it identifies that this is a tail call. It sees the function is about to call itself and then do absolutely nothing else. So it thinks, why in the world would I add a new plate to the stack? I don't need to. So it decides to reuse the current stack frame. It just updates the parameters right there in place, and then, this is the cool part, it just jumps back to the beginning of the function. It's not even really recursion anymore. The compiler has secretly transformed our code into a simple, efficient loop.
In the result of that little trick, it's amazing. We're talking O1 space complexity, constant space. And what that means is, it doesn't matter if your function calls itself 10 times or 10 times million times. The amount of memory it uses doesn't grow. It stays exactly the same. That risk of stack overflow, gone, completely eliminated. Okay, but here's the catch, and it's a big one. In the real world, this magic trick, well, not all languages and compilers actually perform it, which brings us to a tale of two languages, C++ versus Java.
So in the C++ corner, you've got compilers that are all about raw performance. So of course they support TCO. You usually just have to ask for it by turning on optimization flags. But in the Java corner, the philosophy is totally different. The Java virtual machine intentionally says no to TCO. And why? To preserve that full stack of plates for things like security checks, and really importantly, for debugging. It wants you to be able to see exactly how you got where you are.
So what this means for you as a developer is that in C++, you can write this really clean, beautiful tail recursive code. You flip on a flag like -02, and you can just trust the compiler to turn it into a blazing fast loop. You get that elegant design, but with the performance and safety of simple iteration. It's the best of both worlds.
But if you take that exact same logic and write it in Java, the JVM is going to pile up a new stack frame for every single call. No magic, no optimization. The code still looks elegant, sure, but that ticking time bomb we talked about, it's still there. If your recursion goes deep, you are absolutely on a collision course with a stack overflow error.
So, what's a Java developer to do? Just give up on this kind of recursion? No way! They came up with a really clever workaround. Let's talk about Java's trampoline solution, which is all about moving the work from the stack over to the heap.
It's called the trampoline pattern. Here's the core idea. Instead of the function calling itself directly, which grows the stack, it returns an object that represents the next step. Think of it like a recipe. The function just hands you the next instruction. It doesn't execute it. A separate piece of code, a loop, acts like the chef. It picks up each instruction one by one and runs it. The call stack never grows because all the work to be done is stored in these little objects on the heap. And the heap, well, that's a whole lot bigger than the stack. So here's the breakdown. First, our factorial method completely stops calling itself. That's rule number one. Instead, it returns one of two things. If we're at the end, the base case, it returns a trampoline.done object with a final answer. If there's more work, it returns a trampoline.more object, which is basically a little package containing the next step. Then, a separate compute method runs a simple while loop. It just keeps grabbing these more objects and running them until it finally gets a done object. See? No deep stack. We've effectively built our own tail call optimization right in our code.
Okay, that was a lot. So let's wrap this all up. Let's talk about code that thinks ahead and really boil this down to the key takeaways you need to remember.
All right, so what do you really need to remember? Number one, standard recursion is dangerous because the call stack is finite. Number two, tail recursion is the special key that unlocks tail call optimization. 3, TCO is amazing. It turns your recursion into a loop with constant O of 1 space. But 4, and this is critical, language support is everything.
C++ has it, Java doesn't. And finally, number 5, when your language lets you down, patterns like the trampoline let you manually get that stack safety back. You can build it yourself.
So here's my challenge to you. The next time you sit down to write a recursive function, I want you to pause and ask yourself this question. Is this elegant or is it a time bomb? Because now you know the difference. Now you have the tools to decide whether you're writing a beautiful, efficient piece of art or just setting a trap that's waiting to explode.
Today, we're tackling a classic coding mystery, one that really separates an elegant solution from, well, a catastrophic failure. You've totally been there, right? You write this recursive function, it looks perfect, it's clean, it's logical, but you give it a large input and boom, it just dies with that dreaded error. So why? Why does one version work beautifully while another, almost identical one, brings your whole program crashing down? Well, today, we're going to pull back the curtain on how memory really works with recursion. We're going to show you how to write recursion that doesn't crash, and, this is the important part, exactly how interviewers test this critical skill. Okay, let's dive in. So let's start at the scene of the crime, a simple but deceptively dangerous recursive function that pretty much every programmer writes at some point. Take this standard factorial function. Looks harmless enough, doesn't it? But the real killer is this highlighted line right here. Return n times factorial of n minus 1. See, the function absolutely has to wait for the result of factorial n minus 1 to come back before it can do its final multiplication. This unfinished business is the root of all our problems. It means the function's current state, its stack frame, has to hang around in memory just waiting. So what's really happening inside the machine? Well, the system has this to-do list, right? It's called the call stack. And every time the function calls itself, it slaps a new task on top of the stack. Think of it like a sticky note that has the function's local variables, in this case, just the value of n. To figure out factorial of 3, it needs the answer from factorial of 2. So it puts a new sticky note on top for that call. It can't throw away the first note for factorial of 3, because it still needs it to do that final multiplication later. And what you get is this, a tower of waiting tasks, a tower of stack frames, each one holding on to its own little piece of information. Now, for small numbers like 3, this is totally fine. But what happens when the input isn't 3, but 300,000? Does the stack just keep growing? Yes. Is that safe? Absolutely not. Eventually, that tower gets too high. It literally overflows the memory that was set aside for it. And that, my friends, is a stack overflow. Your program is just dead. So how in the world do we prevent this catastrophic failure? Well, we need to restructure our function so it doesn't leave any unfinished business. The trick is to get all the work done before making the next recursive call. Let's see exactly what that looks like. Okay, on the slide here, you can see the two versions side by side. On the left, our old, dangerous friend. On the right, the solution. It's called tail recursion. Now notice the key change. We've introduced this helper function with something called an accumulator parameter. An accumulator is just a fancy name for a variable that carries the results so far along for the ride. The multiplication now happens before the next recursive call. See that? The very final action is just the recursive call itself. There's no pending work. And this is the core idea, plain and simple. There's no, hang on, I still need to multiply by n step. It's kind of like a relay race. Each runner calculates their part of the race and just hands the total elapsed time, that's our accumulator, to the next runner. They don't have to wait for everyone to finish to then add up all the times at the very end. So look at how this one runs. It's completely different. Instead of building a tower of sticky notes, the system sees that once factorial 3, 1 makes its call to factorial 2, 3, that first stack frame, it's totally useless now. It's done its job. So a smart system can just erase the first sticky note and write the details for the second call right on top of it. The stack doesn't grow, it behaves just like a simple loop. But here comes the plot twist. Writing your code this way, well, that's only half the battle. This amazing solution only works if the compiler or the runtime environment is actually smart enough to recognize what you've done. This clever little trick is called tail call optimization, or TCO for short. It's the magic that turns our elegant, recursive code into brutally efficient machine code. The compiler sees there's no need to create a whole new stack frame. So instead of a call instruction, which pushes a new frame, it just uses a JMP instruction, a jump. It literally just goes back to the beginning of the function with the new argument values. No stack growth, no problem. And right here, this is the single most important thing to remember from this entire explainer. The safety of your code depends entirely on the language, the compiler, and even the settings you're using. Just because your code is tail recursive, that doesn't mean it will be optimized. I mean, just look at these different environments. C++ compilers like GCC or Clang, yeah, they'll perform TCO if you turn on optimizations, like with the O2 flag. But the Java virtual machine, the JVM, nope, it typically does not do TCO. So an algorithm that can handle 1 million recursive calls on Linux with GCC might crash after just a few thousand in a standard Java environment. It's the exact same logic, but a totally different outcome. And this isn't some oversight in Java. It's a deliberate philosophical design choice. The JVM prioritizes having a clean, accurate stack trace so you can debug things easily. If it just converted your recursion into a loop behind the scenes, your stack trace would be really misleading. So it sacrifices this specific optimization for better debuggability. This means if you need deep recursion in a language without TCO, you sometimes have to turn to other patterns, like something called a trampoline, which basically moves the to-do list off the stack and into main memory. So how does all this pop up in a technical interview? Well, they're not just testing if you can write a function. They want to see if you understand these critical trade-offs between elegance, performance, and the safety of the environment it's running in. You are going to get a question just like this. They'll show you a piece of recursive code and ask you to analyze its limits. So how do you give a great senior-level answer? A fantastic answer shows you see the whole picture: the code, the compiler, and the runtime, all as one system. You start by analyzing the code itself. Yes, this is tail recursive because the recursive call is the absolute final operation. Then you show your system's knowledge. In a language like C++ with an optimizing compiler, this would be converted to a loop by TCO and would easily handle a large input. However, in an environment like the standard JVM, this would definitely fail with a stack overflow error because TCO is not performed by design. See? You're not just a coder, you're an engineer. So please, avoid these common traps. Don't just assume optimization will magically happen. You have to know your environment. Writing beautiful tail recursion in Java is a noble exercise, but it's totally futile if your goal is to save stack space. And never ever forget to ask yourself if a simple loop would be clearer and safer. Safe recursion is always intentional, never an accident. Okay, let's boil this all down to a simple mental checklist, something you can run through every single time you think about using recursion. Ask yourself these 3 questions every time. 1, is the recursive call the absolute very last thing this function does? No sneaky multiplication or addition after the call returns. 2, do my tools, my language, my compiler, my settings actually support the optimization I'm hoping for? Go check the docs. And 3, is this even the right tool for the job? Sometimes a simple while loop is clearer, safer, and just plain better. And that's the crucial point. You are in control. By understanding how the call stack works, how your function is structured, and how your compiler and runtime behave, you can harness the awesome power of recursion without the risk of it blowing up in your face. So go on, take a look at your own code bases. Now that you know the rules, you might be surprised what you find. Thanks. You've been there, right? You've coded up this beautiful, elegant, recursive function. The logic is just flawless. It sails through all your simple tests, no problem. But then you throw some real-world data at it, and poof, it crashes. So what is really going on under the hood? I mean, it's one of the most frustrating moments for any of us developers. You're just staring at the code, you're tracing the logic again and again, and everything checks out. The bug, it turns out, isn't in your algorithm at all. It's hiding somewhere deeper, down at the system level. Today, we're going to pull back that curtain and find out exactly what's happening. So our mission today is simple, but honestly, it's super powerful. We're going to understand how your code actually runs on the machine. We'll see exactly why good code can fail, and this is the important part. We're going to learn the exact strategies that professional engineers use to build robust, crash-proof recursive functions. So here's our game plan. First, we'll start by digging into this whole crashing code mystery. Then, we're going to dive into the fundamentals of computer memory and specifically the call stack. After that, we'll watch the inevitable collision course between recursion and the stack. And finally, we'll open up the professional's playbook for writing code that's ready for production. Okay, let's set the scene and really define the mystery we're here to solve. The clues you'll see aren't in the code itself, but in that hidden environment where it all runs. The secret to this entire mystery, it all lies in understanding how a computer manages its memory. And for our purposes, we need to talk about two very different areas of memory, the stack and the heap.
Just look at the contrast here. The heap, you can think of it like a giant, flexible warehouse where you can store all sorts of objects that need to stick around for a long time. But the stack is like a small, lightning-fast workspace with a fixed, limited amount of room. Its main job? Managing function calls. This is where our recursive functions live. And its small size, well, that's the root of our entire problem.
Yeah, let's paint a picture of this call stack. Imagine you're at a cafeteria with a stack of plates. When a function gets called, the system puts a plate on top. If that function calls another one, a new plate gets added. And when a function is done, its plate is taken right off the top. This is what we call a last-in, first-out structure, or LIFO. It's simple, it's fast, and it's incredibly efficient. So that brings us to a really crucial question. If this thing is so important for running all of our programs, why on earth would the system limit its size so strictly? And this is just a brilliant example of a core design trade-off in computing. See, when your operating system starts a program, it gives each and every thread its own private stack with a predetermined fixed size. This allows for blazing fast memory management, and it also acts as a safety rail, preventing one buggy, infinitely looping function from eating up all the memory and crashing the entire computer. It's a feature, not a bug. Okay, so we have this small, finite resource, the call stack. And we have recursion, a technique that literally thrives on making many, many function calls. I think you can already see where this is going. It's a collision course. Let's watch it unfold. Every single time a function is called, whether it's recursive or not, a little something called a stack frame gets pushed onto the call stack. This frame holds everything that function needs to do its job, its input parameters, its local variables, and the address it needs to go back to when it's done. So here's the key takeaway. Every single recursive call has a real, non-zero memory cost. Let's look at a real-world example, a simple JSON parser written in C++. To parse a list, the parseList function calls another function, parseValue. But what if a value inside that list is another list? You guessed it, parseValue might turn around and immediately call parseList again, creating this chain of calls that can get very long, very fast. Now, if we parse a simple little JSON array like 1, 2, it's no problem at all. The parser makes a few calls, a few stock frames are created, and they're quickly removed. The stack usage is tiny. It's totally safe. But what happens with a deeply nested input? An array inside an array inside an array, maybe thousands of times. Each one of those opening brackets triggers another recursive call to parseList. The stack grows in a straight line with the nesting depth. One level deeper, one more stack frame. The pressure builds, and our stack gets taller and taller and taller. And then bam, the stack pointer, which is just keeping track of the top of the stack, tries to grow beyond the fixed boundary that the operating system gave it. The hardware itself detects this violation, and the OS terminates your program immediately. This is a stack overflow. It's a catastrophic, unrecoverable error. Your program is done. Now, here's the thing. Not all recursion is created equal. Our JSON parser's stack depth is what we call O of n, meaning it grows linearly, one for one with the input's nesting depth. That is a recipe for disaster. But a classic algorithm like merge sort, it's O of log n. Its stack depth grows incredibly slowly, logarithmically. To sort a million items, merge sort's max recursion depth is only about 20. That's almost always safe. And here it is, the answer to that classic developer mystery. But why does it work on my machine and crash on yours? Just look at the different default stack sizes. Your Linux machine, with its generous 8 megabyte stack, might handle 100,000 recursive calls just fine, but the production server running Windows with its tiny 1 megabyte stack is going to crash and burn with the exact same code and the exact same input. So, to wrap it all up, a stack overflow is usually caused by one of three things. Number 1, a missing base case. That's just a simple logic bug. Number 2, excessive recursion depth, which we just saw with our parser. Or number 3, a more subtle cause, having very large local variables inside your recursive function, which makes each and every stack frame huge. Okay, now that we've properly diagnosed the problem, it's time for the cure. How do professional engineers write that elegant recursive style code that's also safe and robust? Let's open up the playbook. Well, the number one strategy is just to convert the recursion to a simple loop. If that's too complex, you can actually create your own stack data structure on that massive, flexible heap, taking control away from the call stack. Some languages also offer optimizations for a special pattern called tail recursion. And finally, a really simple but powerful defense. Validate your input and just refuse to process data that you know is dangerously deep. So imagine this. You're in a technical interview. They show you a piece of recursive code, just like our JSON parser, and they ask you this exact question. This isn't just a test of your coding ability, it's a test of your system-level understanding. And here is your A+ stellar answer. It shows you understand the why. You're not just fixing a bug, you are addressing the root cause, the call stack's fundamental limitation. You're proposing a solution that moves memory management from the small implicit stack to the large explicit heap, giving you full control. That is a senior-level answer, right there. So let's end with the 3 golden rules of recursion. Rule number 1, correct logic does not equal safe execution. Rule number 2, the call stack is a finite, precious, and limited resource. And rule number 3, always know your maximum recursion depth. Know these rules and you'll never be surprised by a crashing program again.
All right, let's get into it. So, we've all gone through the basics of recursion, right? The base cases, the recursive steps, we get the theory. But knowing the theory and knowing when to actually use it in a real-world professional setting, that is a whole different ballgame. And that's exactly what this is all about, making that leap from the classroom to the code review.
This right here, this is the question that really separates a junior dev from a senior engineer. It's not about can you write a recursive function, it's about should you and why. We're going to build the mental toolkit you need to answer that question with confidence every single time.
So here's the game plan. First, we'll get good at spotting problems that are practically begging for a recursive solution. Then, we'll look at some real-world examples. After that, we dive into the big debate, recursion versus iteration. We'll learn how to talk about our choices like a pro, and we'll wrap it all up with a simple framework you can use every day.
Okay, first things first. You need to know that some problems just scream recursion. I mean, their very structure is recursive. And if you try to force an iterative solution on them, you often end up with code that's messy, way harder to read, and a total pain to maintain later on. Learning to spot this natural fit is skill number 1.
Look at this list: trees, file systems, nested JSON. What's the common thread here? It's that they all contain smaller, identical versions of themselves. It's like they have this recursive DNA baked right in. Recognizing this pattern, this self-similar structure, is your big green light to start thinking recursively.
Let's make this super clear. Just think about a file system on your computer. You have a folder. What's inside? Well, some files, and maybe some other folders. And what's inside those folders? You guessed it, more files and potentially more folders. You see that? The problem of processing a folder contains the exact same but smaller problem of processing a folder. That self-similarity is the signal that recursion might be the most elegant way to go.
All right, enough with the abstract stuff. Let's get practical. Where do developers like us actually use this day to day? We're going to look at a few case studies that really show off how clean and powerful a recursive solution can be when you use it on the right problem.
This is a total classic. You need to scan a whole directory tree, maybe to find a specific file. So you open a folder and look at what's inside. If it's a file, great, you process it. But if it's another folder, what do? You run the exact same logic on that new, smaller folder. That's the recursive call. And the beauty of it is you don't have to manually track which folder you're in or how deep you are. The call stack handles all that bookkeeping for you.
And here's another killer example. You're parsing a gnarly JSON object from some API. You're digging through it, looking for a certain key, but what happens when you find a value that is itself another JSON object? Easy. You just call your parsing function again on that smaller nested piece. This is where recursion is just chef's kiss. Trying to do this with iteration, using your own stack and loops, can turn into an unreadable nightmare real quick.
So we've seen where recursion is a perfect fit. But now we get to the heart of what it means to think like an engineer. Just because you can solve a problem recursively doesn't always mean you should. And this is the professional's dilemma, choosing between the elegance of recursion and the raw safety of iteration.
Okay, let's really unpack this, because this table is where the big decisions are made. With recursion, the call stack manages your state automatically. That's the implicit part. But every one of those calls eats up memory on the stack. Iteration makes you manage state yourself with variables, but you usually have a tiny constant memory footprint. Now, look at the failure modes. This is huge. An infinite recursion doesn't just hang, it blows the stack and causes a hard crash. Your whole program dies. An infinite loop? Well, it just hangs, pinning the CPU. One is a catastrophic failure. The other is a performance problem. Big difference.
This is the question you have to ask. In a textbook, recursion is beautiful. But in production, where you have unpredictable data, massive inputs, what's the tangible, real-world risk we're trying to avoid?
This is the risk. The call stack is not infinite. It's a tiny, fixed-size chunk of memory, usually just 1 to 8 megabytes. And if your recursive function goes just a little too deep, maybe on some weird user-provided data, you will burn through that memory. And the result isn't a friendly error message. It's a stack overflow, a hard crash, game over.
And it gets even trickier, because the language you're using matters a lot. In C++, a smart compiler can sometimes perform what's called tail call optimization, which basically turns your recursive code into a super efficient loop behind the scenes. It totally avoids the stack growth problem. But the Java virtual machine? Nope, it doesn't support TCO. So in Java, every recursive call you make is a step closer to a potential stack overflow error. You're living with that risk.
Which leads us to these major red flags. These are the anti-patterns you have to avoid. First, don't use recursion for a simple, linear job where a for loop is obviously clearer and safer. Second, always think about your inputs. Ask yourself, what's the absolute deepest this thing could go in a worst-case scenario? And finally, please don't just blindly copy-paste a recursive solution from the internet without truly understanding how it's going to impact memory in your application.
Okay, this brings us to a skill that's absolutely critical, especially in a job interview. It's not enough to just make the right choice. You have to be able to clearly and confidently explain why you made it. This is how you demonstrate senior-level thinking.
So when you're in that interview, how do you defend your choice to use recursion? You don't just say, "Oh, it seemed easier." No way. You say something like this. You frame your decision around readability, maintainability, and how the code is a clean reflection of the problem itself. This shows you're thinking about the long-term health of the codebase.
And here's the equally powerful flip side. This is how you justify not using recursion. This answer shows you're thinking about production. You're worried about scalability, robustness, and safety. You're not just solving a puzzle, you're building resilient software that won't fall over when it sees weird data in the wild. So here it is, your go-to mental checklist. Before you commit to recursion, run through these 4 questions. 1. Is it a natural, self-similar fit? 2. Is the logic sound and guaranteed to terminate? 3, and this is the big one, is the stack depth safe for the data I expect? And 4, be honest with yourself, does it actually make the code easier to read and understand? If you can say yes to all 4, you're in a great spot.
Okay, let's bring this all home. The ability to make these kinds of professional judgments isn't something you just pick up overnight. It's built on a solid foundation of understanding what's actually happening under the hood.
You see how it all connects now? You can't make an intelligent decision about stack safety if you don't really understand the call stack from Part 2 or its limits from Part 5. Knowing how to think recursively is step 1, but understanding the performance, the mechanics, and the limits is what gives you the power to make these smart, professional trade-offs.
And if you take one thing away from our time together, let it be this. True recursion isn't just a cheap trick for a loop. It's a profound way of modeling a problem. When you use it correctly, your code is in harmony with the problem's own structure. It's a way of thinking that leads to some of the most elegant code you will ever write. Thank you for joining me today in exploring recursion.